Welcome to another deep dive. Today we are going to be exploring aesthetic mathematics.
Ooh, that sounds fascinating.
It really is. And to help us with this deep dive, we will be drawing insights from Alex Burke's book, Beautiful Symmetry, a coloring book about math.
I love that book.
Me too.
Yeah.
And don't worry, we don't need to be math geniuses to follow along.
Right.
It's more about appreciating how math shapes beauty all around us in snowflakes and sunflowers, even in ancient architecture.
It really is amazing when you start to think about it that way. Like when you
Hmm.
think about it, math lets us explore like perfect symmetry in a way that nature can't always.
Yeah.
And the book goes into that idea
Okay.
by introducing symmetry groups.
Okay, so break that down for me. What exactly is a symmetry group?
So think about all the actions you can perform on a shape
Okay.
without actually changing its overall appearance.
Okay.
Like imagine a square.
Okay.
And now rotate it a quarter turn. It still looks like the same square, right?
Right.
That rotation is one element of the square's symmetry group. Okay.
And if you keep rotating it, you find 4 unique rotations before you're back to the original position.
So a square has fourfold rotational symmetry,
Exactly.
which is a part of its symmetry group.
Yeah. And each of those rotations
Okay.
is a member of what's called a cyclic group.
Okay.
In this case, it would be denoted as C4
C4.
for the 4 rotations.
Got it.
Shapes with the same number of rotations belong to the same cyclic group.
Okay.
So, like a triangle, for example,
Mm-hmm.
would belong to C3 group
Okay.
because it has threefold rotational symmetry.
So C3 for a triangle, C4 for a square.
Exactly.
Okay.
And the book actually explains something kind of interesting about these groups.
Okay.
How coloring a shape can change its symmetry.
Wait, what?
Yeah.
How does coloring change the math of symmetry?
So think about our square again.
Okay.
Imagine you color one half red and the other half blue.
Okay.
Now it only has the symmetries of a rectangle,
Oh.
just 2 rotations.
Okay. So by adding color, you've restricted some of those rotations.
So it's like the colors locking certain parts of the shape,
Exactly.
preventing those symmetry operations.
Yeah.
Okay.
And this actually leads to another concept
Okay.
called generators.
Generators.
Yeah. Think of a generator as a single rotation
Okay.
that, when applied repeatedly, it'll produce all the other rotations in the group.
Okay.
So, for example, a 1/3 turn generates all the rotations of a triangle.
Right, because if you rotate a triangle by a third 3 times, you're back to the starting point,
Exactly.
hitting all the symmetric positions along the way.
Yeah. And then you also have the idea of subgroups.
Okay.
So these are groups nested within other groups.
Okay.
So like our colored square is a good example.
Okay.
It started as C4,
Right.
but then the coloring reduced it to C2, which is a subgroup of C4.
I'm following along. So far, we've only been talking about rotations, but what about reflections?
Right.
Like mirror images, those are symmetries too, right?
Absolutely.
Okay.
Reflections or mirror symmetry add a whole other layer of complexity.
Okay.
When you combine reflections with rotations, you get what are called dihedral groups.
Okay.
They're denoted as D3, D4, and so on.
So we're like leveling up the symmetry game. Like more symmetry operations means more complex groups.
Exactly. And here's where it gets really interesting.
Okay.
Dihedral groups are non-commutative.
Non-commutative.
Yeah. It means the order you perform the operations matters.
Okay.
So reflecting a square and then rotating it
Mm-hmm.
gives you a different result than rotating and then reflecting it.
So the order of operations matters now. We can't just shuffle them around.
Exactly.
Yeah.
And just like with the rotations, coloring can also reduce a shape's dihedral group to smaller subgroups,
Okay.
including those with only reflections or only rotations.
So the coloring can strip away either the reflections or rotations.
Exactly.
And leave a simpler symmetry group. It's like a visual puzzle, seeing how you can simplify the symmetry with color.
That's a really good way to think about it.
Yeah.
It shows how visual changes can directly impact the underlying mathematical structure.
Okay.
Now, are you ready to go beyond individual shapes?
Yeah.
And look at how this applies to like repeating patterns,
Okay.
like friezes and wallpapers.
I am ready to expand our symmetry horizons.
Okay. Let's dive into the realm of infinitely repeating patterns.
From shapes to infinity and beyond. I'm ready.
Awesome.
Okay, so we're stepping into the world of repeating patterns. Where do we even begin?
Well, first we need to add a new symmetry operation to our toolkit, translations.
Equations, okay.
Which basically just means shifting the whole pattern
Okay.
without changing its appearance.
Gotcha.
So picture sliding a tile pattern across a floor.
Okay.
It's the same pattern,
Right.
just in a different location.
Like those moving walkways at the airport.
Perfect analogy.
Okay, cool.
Now, here's a mind-bending fact from the book.
Okay.
Even if you like color half of an infinitely repeating pattern, basically you're removing half the translations.
Okay.
You still have infinitely many translations left.
Whoa.
Oh.
So infinity divided by 2 is still infinity.
It is.
Okay, my brain hurts.
It stretches the imagination,
Right.
but it really highlights the power of infinity when it comes to these patterns.
Okay.
Now let's narrow our focus to friezes.
Okay.
So these are the patterns that repeat in one direction, like
Okay.
those decorative borders you see,
Okay.
or tile work, things like that.
Okay.
Friezes can have the symmetries we've already talked about, the
Yeah.
translations, the rotations, reflections.
Love it.
But they can also have what are called glide reflections.
Glide reflection.
Yeah. So imagine reflecting the pattern
Okay.
and then sliding it along the line of reflection.
It's like a reflection plus a shift.
Exactly.
Okay.
And when you combine all these possible symmetries
Okay.
in different ways,
Okay.
you actually end up with 7 distinct frieze
Something
groups.
like
Each one represents a unique way that these symmetries can interact to create a repeating pattern.
7 basic blueprints for a whole world of frieze designs. That's pretty cool.
It is. And these frieze groups, they pop up everywhere, like
Everywhere.
from architecture to textiles.
Hmm.
Once you start noticing them, you'll see them everywhere.
I can imagine. Okay. I'm ready for the next level, wallpaper patterns.
Okay.
Repeating in 2 directions, not just one.
Right.
So I imagine the symmetry possibilities get even wilder.
Oh, yeah. You're in for a treat.
Okay.
Wallpaper patterns are where things get really complex and beautiful.
Okay.
So we still have translations,
Okay.
but rotations are a bit more restricted
Okay. How so?
because the pattern has to like fit together seamlessly
Oh, yeah.
in a repeating grid.
Right.
You can only have rotations of a half, a fourth, a third, or a sixth of a turn.
Why those specific fractions? Why not say a fifth of a turn?
Well, it comes down to geometry.
Yeah.
So if you try to like tile a plane with pentagons,
Okay.
which each have that 5-fold rotational symmetry,
Okay.
you can't do it without gaps. But squares, triangles, hexagons, with their
Mhm.
respective rotational symmetries,
Yeah.
they fit together perfectly.
It's like a geometric puzzle, like only certain rotations allow the pattern to repeat without leaving holes.
Exactly.
Oh, yeah.
So with these restrictions on rotations and all the other possible symmetries, we actually end up with 17 unique wallpaper groups. 17. It's like this symphony
Wow.
of translations, rotations, reflections, and glide reflections all working together
Wow.
to create these endlessly fascinating designs.
17 unique ways to tile a plane with symmetrical patterns. That's incredible.
It is.
I bet those patterns are hiding all over the place just in plain sight.
Oh, absolutely.
Yeah.
From ancient mosaics
Mhm.
to modern wallpaper designs,
Wow.
these 17 wallpaper groups are like a testament
Yeah.
to the power of symmetry
Okay.
in art and design.
But it's not just about aesthetics.
Right. This underlying mathematical structure,
Okay.
it plays a crucial role in things like crystallography. Okay.
Where scientists are studying the arrangements of atoms in solids.
So the same patterns that make beautiful wallpaper also govern the microscopic world of crystals.
It is.
That's mind-blowing.
It really highlights a key takeaway from this deep dive.
Okay.
Math isn't just some abstract concept.
Yeah.
It's this language
Yeah.
that describes the very structure of our world,
Yeah.
from the tiniest atom to the vast expanse of the cosmos.
Speaking of math not just being abstract, the book talks about another concept, inverses.
Oh, yeah.
Can you explain that a bit?
Absolutely. So for every symmetry operation,
Right.
there's an inverse operation
Okay.
that brings the shape back to its original position.
Okay.
So like if you rotate something clockwise,
Okay.
then rotate it counterclockwise the same amount.
Mm-hmm.
You're back where you started.
It's like hitting the undo button on your symmetry operations.
Exactly.
Like no matter how many times you transform the ship, you can always get back to the beginning.
Exactly.
And this interplay between these operations and their inverses is really part of what makes these patterns so fascinating.
Okay.
This beautiful dance of transformations,
Yeah.
always balanced, always harmonious.
Okay, we've gone from basic shapes to infinitely repeating patterns.
We have.
Talking about rotations, reflections, translations, glide reflections, even inverses.
Yeah.
My head is spinning, but in a good way.
And the best part is
What?
we've only scratched the surface.
You mean there's even more to learn about symmetry?
There is.
I'm both excited and terrified.
It's a big world out there.
And it's a big world.
Full of symmetry.
Okay, so we've uncovered all this amazing, mathematical structure behind these beautiful patterns, but it still feels kind of abstract.
Yeah.
How do we connect this back to the idea of, aesthetic mathematics?
Well, that's the beauty of it.
Yeah.
Once you start seeing the world through this lens of symmetry, you begin to understand how these mathematical principles actually shape the beauty we see all around us.
It's like we've been given a secret code book to decode the visual world.
Exactly.
Suddenly these patterns that seemed random or purely decorative, they have this deeper layer of mathematical meaning.
Exactly. And that's where the real appreciation for aesthetic mathematics comes in.
Okay.
It's about recognizing that, those same mathematical concepts that govern the shape of a snowflake also influence the structure of a sunflower, a seashell, even a spiral galaxy.
It's like the universe is speaking to us in the language of math.
I love that.
And these patterns are like the visual representation of that language.
Absolutely. And the book actually does a really good job of visually representing these concepts.
Okay.
The coloring exercises actually help you understand the interplay between shapes, colors, and symmetry in a really tangible way.
Okay.
It takes what could be a very abstract subject and makes it accessible and engaging.
It's one thing to read about rotations and reflections. It's another thing entirely to actually color in a pattern and see how those transformations come to life.
Exactly. And that active engagement is key to developing that deeper appreciation for the beauty of the math involved.
Okay.
It's no longer just equations on a page. It's a visual experience that sparks curiosity and wonder.
So what's the biggest takeaway you hope our listeners get from this deep dive?
I really hope they come away with a newfound appreciation for the fact that math isn't just about numbers and calculations. It's a language that describes the very essence of beauty.
Okay.
A language that's woven into the fabric of our world.
Yeah.
From the smallest atom to the grandest cosmic structures.
Math is the invisible hand shaping the beauty we see all around us.
It is.
And once you become aware of it, it's hard to unsee it.
Right.
You start noticing symmetry and patterns everywhere.
Absolutely. And that's the exciting part.
Yeah.
It opens up this whole new way of seeing the world. So as you go about your day, I really encourage you to pay attention to those details.
Okay.
Look for the patterns and symmetries that might have gone unnoticed before.
Okay.
Notice the repeating patterns in brick walls, the arrangements of petals in a flower, the delicate balance of a spider's web.
Wow.
You'll be amazed at what you discover.
It's like a treasure hunt for hidden mathematical beauty.
Exactly. And here's a final thought-provoking question for you.
Okay.
As you're observing all these patterns, do you see any that don't quite fit into the categories we've discussed?
Oh.
Are there patterns that seem to break the rules to defy categorization?
That's a great challenge.
Yeah.
It makes you realize there's always more to learn and discover.
Yeah.
The world of aesthetic mathematics is vast and endlessly fascinating.
Precisely. And that's what makes it so exciting.
Yeah.
This deep dive is just the beginning of the journey.
Okay.
There's a whole universe of symmetrical exploration out there just waiting to be discovered.
Thanks for joining us on this incredible deep dive.
Yeah.
Into the world of aesthetic mathematics. I hope you're feeling just as inspired as I am to look for that symmetry.
Yeah.
Those patterns, that mathematical beauty everywhere you go.
Happy exploring.